to okay, so it's my pleasure to introduce Dan. We'll talk today about a new Lie theory for simple Lie superalgebras.
Okay, thanks. Let's see. Can you guys? I'm not sure how this is set up. Can you see me at all? I know you guys can see me. Can people see me out in the audience or no? There's someone shaking their head no.
We can see you very tiny with a huge, from the very far back of the room, way zoomed out view of the room.
Oh, you only zoom in. That's... So I've done this before. Okay. All right, so let me see if I can like point. Let's see. Oh, got the other way around. Okay, how's that, Brian? Better?
Yep, we can see you bigger now.
All right, great. Okay. Good. All right, so I'd like to first thank the organizers, Scott and Arik. I'd like to actually thank them for their efforts this semester and actually this entire year. I think they've done a really great job. In this talk, what I'd like to do is I'd like to give you sort of a blueprint or sort of an outline of what's been happening in terms of simple superalgebras. And it's kind of an exciting time because we've sort of rethought the development of the subject, and I'd like to sort of give you a survey on some of the highlights. Okay, so let's advance the slides here. Okay. All right. So as many of you know, Jim Humphreys passed away on August 27, 2000 due to COVID-19. When I was actually constructing this talk, I thought about how I learned the basics of Lie theory, and two books came to mind. And so the first one is this classic from 1972, Introduction to Lie Algebras and Representation Theory. This is the one we use at the University of Georgia when we teach our graduate course on Lie algebras. And during this talk, I'll also use his other book on conjugacy classes and semisimple algebraic groups. Jim was a very important mathematician in the area of algebraic group representations. His books and expository articles were instrumental in the development of the field. Jim was also very supportive of younger mathematicians in representation theory. We actually were both students of George Seligman. He was much older than I was, and he sort of took me under his wing as a sort of younger brother. When I first entered the field, Jim wrote an extensive math reviews on my PhD thesis on projective modules over Lie algebras of Cartan type in 1990. I will always be indebted for Jim's words of encouragement, careful reading of my work, and his guidance over the past 40 years. All right, so where I want to start my talk is at a place where I think people are sort of familiar with. This is sort of the type of exposition you would actually see in the first Lie algebras course. So let G be a complex simple algebraic group. G be its Lie algebra, and you take a maximal torus inside of G. And with that maximal torus, you're able to make a triangular decomposition for your Lie algebras. And the n minus and n plus, these consist of root vectors. And once you actually have these root vectors, you axiomatize the properties of roots. Once you make those axioms, you actually form what's sort of define what's called a root system. And for a simple Lie algebra, you get an irreducible root system. And then once you have the absence root system, you can actually classify them. And so that actually classifies the complex simple Lie algebras. We have the infinite families A, B, C, and D, and then the 5 exceptional families. All right. Now, what goes into the classification? So one of the important things that we use in the classification is the notion of semisimple and nilpotent elements. So it turns out that whenever you take an element in the Lie algebra, you can break it up uniquely as a semisimple element and a nilpotent element, and the semisimple element and the nilpotent element. So the way one might want to think about this is like in GLN, you can actually conjugate the X in terms of a nice Jordan canonical form, where the semisimple part turns out to be the eigenvalues, and then the nilpotent part turns out to be the Jordan block associated with that. Okay. And then to describe all the semisimple elements, you just have to take a maximal torus and saturate it with G. So the first thing I want to talk about, well, before I talk about that, let me talk about the nilpotent elements. So you also can talk about nilpotent elements. The nilpotent elements form an affine algebraic variety, sometimes called the nil cone. Gx on n via the adjoint representation. So for GLN, it's just conjugation of matrices. It's well known that the number of orbits on n is finite, and the orbits can be classified. So like with GLN, you can just classify them via partitions of n using Jordan block sizes. In general, you can do this for the classical type of the algebras, and then you have other classification ways using weighted Dickin diagrams, and also the Borel-Carter classification. All right, now we'll actually move on to sort of semisimple elements. All right, so I want to remind you of a important theorem. This is the Chevrolet restriction theorem. So if you look at the symmetric algebra on the dual of the Lie algebra, and you take the G invariants, you can look at the restriction map from S of G star to S of T star and take the Weyl group elements. And the theorem says that this restriction map with the invariants is an isomorphism. So this is really a theorem about the semi-simple elements. This theorem is really useful because it allows you to actually describe the center of the universal enveloping algebra, and also to determine the blocks for category A. Now, what you can also do with this, will also conclude, is that the symmetric algebra for the G invariants is in fact a polynomial algebra. All right, so that sort of describes the Chevrolet restriction form. Now, let me just kind of give you some facts about the nilpotent cone. The nilpotent cone is an irreducible conical variety. You can obtain it by saturating the nil radical of the Borel by G. The dimension is just twice the dimension of n plus, which is equal to the number of roots. And then there's a very nice desingularization for n, and this is called the Springer resolution. This appears a lot in our seminar, and it's used in geometric representation. And this pi is just given by sort of multiplication. All right, now what I want to do next is I want to actually connect the semi-simple part involving the Chevrolet restriction theorem with the nilpotent cone. And so you can get this relationship as follows. So if you have the nilpotent cone, and G is a connected reductive algebraic group, such that script P is equal to Lie of G, then the nilpotent cone can be realized as just the G invariant polynomials without constant term. So there's zero set of that, and that gives you actually the nilpotent cone. So when you want to write the coordinate algebra, then it's just the quotient of the symmetric algebra on G star with the ideal generated by these invariant polynomials. And so there's actually something even stronger you can say. This involves what's called the harmonic decomposition. So you can actually write the symmetric algebra on G star in terms of the G invariant polynomials tensor of the coordinate algebra on the nilpotent cone. So there's a really tight relationship between the semi-simple elements and the nilpotent elements. in terms of algebras. That's what this is actually saying. And so we'll actually come back to this later on. All right, so let me pause right now. Are there any questions on the first part of this talk? Okay. All right, so the next thing we want to do is we want to move on to superalgebras. So this is a slide that you've seen before. It's recycled. So what's a Lie superalgebra? It's basically a Z2 graded vector space with a bilinear operation. This is the bracket or super bracket. And the first axiom says that you have this skew commutativity. And then the second axiom that I put down is a form of the Jacobi identity, and it's called the super Jacobi identity. Now, the important fact about these superalgebras you should always keep in mind is that G0 bar is a Lie algebra. It's a Lie subalgebra of G. And if you take the group associated with G0, right, called capital G0 bar, then this acts on G1 bar via the adjoint action. And this action is quite important to study, because if you know certain things about this action, then you can actually use some geometric invariant theory to make some very nice constructions. All right, so let me give you the sort of most standard Lie superalgebra. So what you do is you define the general linear Lie superalgebra as follows. So you take m plus n by m plus n matrices, let's say over the complex numbers. So what is your zero component? Your zero component will just be the block diagonal matrix, block matrices on the diagonal. So your G0 is GLM cross GLM, the direct sum GLM. Okay, so that's just given by AB up here. And so what are your odd elements? Well, your odd elements are just the things which are not on the diagonal blocks. So you get the matrices of C and D there. And G0 will act on little G0 just by conjugation. Actually, it's not quite conjugation, but it's sort of close to conjugation. And then G1, also act on G1, okay, in a very sort of standard way. And so the supercommutator, you just have to keep track of signs. And so EIJ are just the elementary matrices. And so notice that we have this additional factor -1 to the EIJ bar, EKL bar there. Yeah, so this additional, see if you can see it on the screen when I do this. Can you see that? Okay. So this part over here keeps track of the signs. Okay, so without it, you just get the ordinary relationship for the general linear Lie algebras, for example. But for GLMN, you have to keep track of the signs using this. All right. Now, it turns out you can also classify simple Lie superalgebras. And Katz did this in 1977. Now, this doesn't just go along the same lines as with complex simple Lie algebras. There are these additional families, and there's also the Cartan type Lie superalgebras. So this is more reminiscent of the type of classification that you get in characteristic P when you try to classify simple Lie superalgebras. Okay, so in this talk, we're not going to worry so much about the Cartan type Lie superalgebras. We'll be interested in are the ones which are called classical. And the ones which are classical are the ones where G0 is a reductive algebra, G0 bar. And so G0 bar will act on G1 bar, and these classical simple Lie superalgebras. So I'm lying a little bit because not all these are simple in terms of the strict definition of simplicity, but they sort of are close enough to being simple. So the standard ones for like type A are just GLMN, SLMN, PSLMN. And then for types B, C, and D, you get these families involving OSPMN. And then the exceptional types are the ones of type D, G3, and F4. And then there are these kind of, I guess, queer or strange, periplectic, these superalgebras, they're called different names. And these are ones of type QN and type PN. Okay, so this gives you a list of these simple Lie superalgebras. All right, so I'm going to ask the following question. So we have this nice theory for complex simple Lie algebras. So the question is, can we actually formulate a theory like the one for complex simple Lie algebras for these Lie superalgebras? So what we like is we like to have a triangular decomposition. We like to be able to sort of factor G as a plus part, a minus part, and then something in the middle. Okay. Now, it's known that you just can't take a maximal torus. Right? So that we may have to give up complete reducibility in order to find this factorization.
When you say you can't take a maximal torus, so through GLMN, these values can be
For GLMN, it does work, but for type Q, it doesn't. Okay, well, that's a good question. So for some of them, it does work, but for other types, it doesn't work. And so we want to adjust the theory so that it will work for all types. Okay. All right, good. And then once you have a decomposition like this, can you actually sort of find a new lead to unify the representation theory of these superalgebras and not study these algebras on a case-to-case basis? So a lot of the literature on these superalgebras involves taking a particular Lie superalgebra and studying its representation theory and writing a paper on that Lie superalgebra. What we want to do here is we want to actually unify the entire theory. I mean, is there a commonality that we can use like we actually study complex semi-simple Lie algebras? Okay. All right. So in order to start off, I have to start the story off about 15 years ago. So this is work that was done when John Kujawa was a postdoc here at UGA with Brian Bowe, myself. And so we wrote a series of papers on these detecting subalgebras. So it turns out that something really nice happens for classical superalgebras. So by using the action of G0 on G1, you can study the type of actions that you have. So you can have what are called stable actions, which actually happen, I think, in all cases. And a little bit stronger situation is when you have what's called a polar action, as defined by Theodok and Katz. And so when you have these actions, you can actually find a subalgebra, a Lie super subalgebra inside of G. And these subalgebras turn out to be much smaller than G itself. So, for example, when you have a stable action, you have a subalgebra which is isomorphic to copies of SL11, or sometimes GL11. And the beautiful thing that happens is that on the cohomological level, the subalgebra detects all the cohomology. So when you take the restriction map in the cohomology, so this is relative cohomology, then the restriction map is actually an isomorphism. So this should actually hint at a theorem that I showed you before. Now, in the case of a polar action, you can find a subalgebra isomorphic to copies of Q1, such that the restriction map is also an isomorphism. Right?
What if we do that?
So N is a reductive group, and it's sort of it's going to be sort of a normalizer of this action on certain elements. So it turns out it will be reductive. So, like I said, you'll see in a second. All right, so I think this will now put it in more of a context. So if you notice this slide, the bottom level should look pretty familiar. The bottom line is very much like the Chevrolet restriction theorem. So in superalgebra theory, when you take these detecting subalgebras, you get a Chevrolet restriction type of theorem, which is down on the bottom. Okay? But moreover, you can sort of functorialize the Chevrolet restriction theorem. So the restriction maps turn out to be just restrictions in cohomology. And this turns out to be quite powerful. Okay?
So actually probably all the odd dimensional cohomology data for
no, it actually, for Qn it doesn't. But for the other types it does. Okay, but for type Q it doesn't. Yeah, type Q is a little bit strange, but still it's encapsulated in this thing.
but bottom line is all
No, the bottom thing, this thing,
oh, that's the odd as well.
it could be on. Yeah, in fact, I mean, this does cause some headaches sometimes. So in our latest paper, we had to deal with that situation. Yeah, so this is just all degrees. Okay. All right, good. Any other questions? All right, that's good. Let's see. All right, so I also want to mention one more thing is that, you know, the E, this is very much like representations of finite groups in characteristic P. So the way you should maybe think about the E is it's sort of like an elementary being, or like a CELO subgroup. So in the theory of superalgebras, there's this sort of local global type of phenomenon that's also happening. All right, so let me just give you some concrete examples. All right, so this is a slide that's been used before too. So what does an F look like? Well, let's say I take GL3 2. So notice that the F0 here is a torus, not necessarily a maximal torus, inside of G0. So if you notice F0 here just consists of diagonal matrices. Okay. And the thing is, with your odd part for the F, you also have to complement things with sort of diagonals sort of above and below the diagonal in the odd sections. Okay. So you can see that you just can't use a maximal torus for this F. You actually have to use some odd degree terms too. So, you know, one way to actually think about this is maybe this is a type of odd torus. All right, now when we wrote these papers, we had a conjecture from 2008. And so because your cohomology ring is a ring of invariants on a polynomial algebra with a reductive group, the cohomology is finitely generated. So with the finite generation of cohomology, you can talk about support varieties. And you can sort of define support varieties in sort of a natural way. On the bottom is sort of the definition of support. So what do? You just look at the action of cohomology ring on X to M, thing that you see many times here. And then you just see which primes inside the spectrum localize. So this gives you the definition of the support variety. And you can also define the support variety for E and F. And you can look at the map on supports. So it's not hard to show, like in part B here, that this map on supports is actually injective. Okay, that's not hard to show, actually, just using the definition. So the conjecture is that or at the time, was that the restriction map on supports actually gives you an isomorphism once you do the correct factorizations. So here you have to sort of factor by the action of the finite reflection group. Here you sort of have to factor by n, whatever that means, in terms of geometric invariant theory. And then here you just get the regular support. And the advantage to this, if this theorem or conjecture is true, is that this support given by GG0 is very difficult to compute. The support involving E and E0 is just given by some rank variety description. And so it has a very, very concrete description. So once you have this isomorphism, you can actually prove like the tensor product property on support varieties. Okay. Now, this conjecture was actually verified in type 1 new superalgebras by Lear, Zhang, and myself in 2010. And there was a lot of evidence for the validity of this conjecture, even back in 2008. Okay. All right, so what are these varieties good for? So Katz and Wakimoto made a definition back in 1994. This definition is just purely combinatorics. So if you take a weight on maximal torus, then the atypicality will just be the number of linearly independent, mutually orthogonal isotropic roots, such that the inner product is lambda plus rho. So rho is the half sum of even roots minus the half sum of odd roots. So it's similar to the ordinary case. Okay, so you just want to see when this inner product is actually equal to 0. And this was only stated for basic classical superalgebras. So one with a non-degenerate trilinear form with a lot of adjectives attached to it. I'm not going to say what all the adjectives are. All right, now there's also this invariant atypicality. A lot of people have studied this in superalgebra theory, and there are various combinatorial algorithms to calculate the atypicality of things that have been developed. Okay, so I think I mentioned this. And so we actually conjectured, or actually we proved this over the course of some years. So we showed that the atypicality can be just measured by the dimension of the support on an irreducible representation or any basic classical superalgebra. Okay, so BKN did this for GLMN, and Kujawa, I believe, did this for the OSP types. And the for the exceptional types, it's not hard to actually prove this. Okay. Now, for types Q and P, it's actually, there are various definitions of atypicality which are floating around. And no one knows like what the best definition is for atypicality in those cases. So I've given this talk a couple of times, and the way I sort of tell this is the following. So today I want to start a revolution. So you could be on the left or on the right, whatever, but I want to start a revolution. I don't want you to go out and do anything after this talk, by the way. So, so you heard it here first. I want to make a new definition of atypicality that doesn't depend on lambda. So the new definition is as follows. So this is not going to hold for just basic classical algebras, but just arbitrary superalgebras in general. And so I want to define the atypicality of the module to be just the dimension of the support value. Now, what's the advantage of this? Well, one advantage is it's completely functorial. And we don't have to just worry about irreducible representations anymore. We can just define this for any representation that we want. And so I think it would be an interesting problem to figure out what combinatorial description this definition would actually give in types P and Q. So you can certainly define it. It's very well defined. So how can you describe it for irreducible representations in type geometry? Maybe Brian knows the answer to this. Okay. All right, so these support varieties, they don't actually detect projectivity, but they actually are a reflection of what's called the atypicality. So it turns out that if you take a projective module, the atypicality will be 0, but just because the support variety is 0 does not mean it's a projective module. There are examples of non-projective modules where the support is actually equal to 0.
Is there any other information you have?
It turns out to behave somewhat well with respect to like short exact sequences. It behaves very well with respect to tensor products and direct sums.
But it's like, for example, there's different ways to have you ever gotten any information about using which of the bits it might be?
So historically speaking, the supports have been used to actually give it weights of nodes and like projective resolution. So it turns out the greater growth of that minimal resolution, projective resolution, equals the dimensions. So it's basically the dimension of the right. But I mean, there are other applications too. But they're a little bit more subtle. They're also very useful for classifying like big tensor ideals and computing what's called the Balmer spectrum. So using things in tensor triangular geometry. So once you have a good support theory, then I can actually tell you more about the ideals in your calculus. All right, let's see. Pause for a second. Okay, so now we sort of talked about the semi-simple side of the story. So what about the nilpotent side? All right, so this is more recent. So we can define the nilpotent cone just like we would for complex semi-simple algebras. So what do? You take the G0 invariant polynomials on the symmetric algebra on G1+, the ones without constant term, and then you look at the 0 sum. Right, so this actually is not a new idea. I mean, this was motivated by work of Victor Katz in 1980, where he defined the nil varieties for general graded least superalgebras. He did this in exactly the same way.
There's no part of the nilpotent code lies in G0, it all lies in G1.
You can do it that way.
What I'm just because the problem with the nilpotent stuff in G0 doesn't restrict this.
Well, the thing is, you look at the harmonic decomposition. Okay, there's a harmonic decomposition of S of G1 star. And it's S of G0 star G0 invariance tensor the coordinate algebra. This is the type. So when you use the G0 action on G1, it's natural to look at this one.
No, I guess I would put the G0 action on itself. Doesn't restrict this.
Not for this side of the story. Okay. I mean, it might.
No, I would thought just naively, some nilpotent part in G0 as well. Like G0 itself, I would expect it naively.
So the thing is, it's the odd elements that you just want to look at the odd elements. This is
the odd elements. You know, I guess this is sort of like the odd part.
There isn't even nilpotent.
This is like the odd.
Yes. And it sort of complements the detecting subalgebra story. Right. If you look at the Chevalier restriction theorem, the classical Chevalier restriction theorem, this is the sort of the natural object study. All right. All right, so this is work that's actually been spoken on by Andy Jenkins. And so what did we prove? We actually proved that this nilpotent cone has finitely many G0 orbits. just like with the classical group. And so for GLMN, we actually have a complete classification of orbits with explicit orbit representatives. And back in 2005, Duflo and Serdanova actually constructed what's called the self-commuting variety. And this variety is used a lot in superalgebra representation theory in order to construct what's called a Duflo-Serdanova function, using getting certain equivalents of categories. And so, so we actually proved the following. So if you take their variety, their self-commuting variety, it actually sits inside the nilpotent count. And for basic classically superalgebras, Duflo and Serdanova proved that their variety has finitely many G0 orbits. So as you can see, we were able to actually generalize this because our theorem actually obtains their theorem, but it also obtains it for all classical simple superalgebras. And something else that you can also glean from this picture is that, and the script X has been quite important for the theory. But we think actually script N might be even more important because it's a bigger variety. It actually contains X, and so naturally you think we have more information. All right. Now, for a long time, we were I don't know if we were stuck or we just there were not too many varieties. So you had these detecting subalgebras, and we didn't know how to get from sort of the detecting subalgebra up to the entire Weyl algebra, the superalgebra. So we had to sort of come up with a way to do this. And this is where the BBW parabolic subalgebras come in. All right, so this is where it was started, introduced by Grantcharov, Grantcharov, myself, and Jerry back in 2019. So Nikolai and Jerry were undergraduates at UC Berkeley at the time, class of 2019. The project actually started in 2018. My daughter was also, Susanna was also an undergraduate at UC Berkeley, and actually introduced Jerry to me, who wanted to actually work on some mathematics. And so much of this project was actually accomplished at MSRI in the spring of 2018 when I was visiting. So a lot of things sort of had to line up for this project to sort of take place. So we defined these parabolic subalgebras, which I'll kind of describe in a second. And one of the things we were able to do with these parabolic subalgebras was we were able to find a nice decomposition. So whenever you take a classical superalgebra over C, and let F be the detecting subalgebra, there's a nice parabolic that you can attach to F and N minus, let's say, so it's going to be the negative parabolic, such that you get a very nice decomposition of your superalgebra. And this B is called a BBW parabolic subalgebra. You'll see why in a second. All right. Okay, so let me just give you an example of this. So for GL33, your F looks like this. Right? So you have, in this case, since N and M are the same, your F0 is just going to consist of like things on the diagonal, right? And then you have to look at the F1 part, which will consist of things on the diagonal in the blocks, in the odd blocks. Okay. So this is the natural super subalgebra. And then to get the decomposition now, you just take the things sort of above the diagonals of each of the blocks. Okay. Now, this is nice because like in type Q, you don't get a triangular decomposition. Well, you do when you do this. But it turns out that in general, if you just take the maximal torus, you don't get a triangular decomposition. You actually have to take this F together. Okay. Now, since we have a Borel, or something like a Borel, the natural thing to try to sort of think about is sort of sheaf cohomology. So just like with the Borel-Weyl theorem, you want to look at sort of induction from B to G. You want to look at global sections. You think about this, and you want to be able to say something about the global section function. Okay, so G will be the algebraic supergroup. Actually, you have to do supergroup schemes, so something a little more technical. So there's an algebraic supergroup scheme which is associated to this Lie superalgebra G, and then for the B, this BVW parabolic, there's also a supergroup scheme associated with that. So we want to look at induction from this supergroup scheme B up to G. Okay, so now you can look at these induction functors. So this is like, these are like the functors that we studied in representation theory algebraic groups class last fall. And you can look at the higher right-to-right functors of induction. And for now, I just want to look at what happens with the trivial model. So you take the Poincare series associated to this cohomology. So you just take the higher right-to-right functors of induction from B to G of the trivial module, and then you put a T to the N in to sort of keep track of degrees, put the dimension here, and then you get this Poincare polynomial. And this will die above the dimension of G1, okay? Just like normal. Now, it turns out something very interesting happens in the super case. Kemp's vanishing theorem doesn't work. So what we'll do is we'll see later that there could be higher sheaf cohomology with us. So in the classical case, it doesn't happen because the weight is dominant. But in this case, it turns out that you can have higher sheaf cohomologies. All right. Now, what's also important to look at is to look at the Poincare polynomials for the superalgebra cohomology for G and the superalgebra cohomology for B. And you can just take the quotient of these Poincare series, P of P, T over P of G. All right, so what did we actually prove about these Poincare series? So we're able to show the following. So whenever you have this setup, and we have to be careful. We can't apply this to type Pn for n bigger than or equal to 4. The reason why it doesn't work for Pn is that the decomposition is not symmetric. Okay, so the weights are a little bit sort of asymmetric. And so for the other types, everything is nice and symmetric, but for Pn, it's not. So that's why we have this condition up here. So there exists this parabolic subgroup and the superalgebra associated to it. So the first thing you can say is that it decomposes rather nicely. And the decomposition is nice with respect to the even and odd parts. And so for the odd part, the B0 is just a Borel subalgebra for the G0 component. Okay. And then when you look at the cohomologies, then you get like a harmonic decomposition here. So you can write the cohomology for B as a tensor product with the cohomology for G and the gradient on the group algebra of W1 bar. And W1 bar is some kind of reflection. And the beautiful, something very beautiful happens. So if you look at the sheaf cohomology and its Poincare series for the trivial module, then it turns out that you can identify this with the Poincare series for this finite reflection group. It's given by lengths of elements. And you just specialize this S at a power of T. So for Qn, you just make S be equal to T, But for the other types, you have to use T-square.
So TPE is, what are the two things on the left side? TPE is DPE.
Yeah, so those are what we're on the left side.
Okay, sorry.
Yeah, yeah. So it's just a motion. Which kind of makes sense from the decomposition.
Okay, capital D or
It was the.
okay, sorry, yeah, sorry, I didn't, right, okay.
No, no, it's hard to slide.
Oh, that's actually, I didn't know.
Okay. Okay, so this one's a sheaf cohomology sort of Poincare series. This one is the sort of relative cohomology quotient Poincare series, and they all sort of match up. Okay, good. All right, so let me say a little bit more on, in an example what W1 is. All right, so here's how you construct W1. You take, you have a reductive group sort of obtained by using the stable action. You take the normalizer of that modulo connected component, just get W1. This is a subgroup of the Weyl group for the even part. Okay. And so here's an example. So if you take GLNN, what is the Weyl group for GLNN? The even Weyl group, which is symmetric group cross symmetric group. And this W1 bar is the symmetric group here, and it's just embedded diagonal inside. Okay. So you get these nice embeddings of W1 inside the even Weyl group for the G0. Okay, so it's a nice, it's very computable in terms of what you've got. All right, so I'm just going to give you sort of some of the ingredients that go into these computations. So I'm just going to go over this fairly quickly. So in order to actually do any computations, you need to actually restrict your cohomology groups down to G0. And when you do that, you can sort of replace your bundle by something slightly more complicated involving the exterior powers of G1 over P1 star. And so what's the advantage of doing this? Well, under certain conditions, you can actually do this. And then you can apply the Black-Morel-Bay theorem to actually do the computation. Because of E0 to G0, that's possible. And that this allows us to actually use the action of even Weyl group on odd groups. And that's what's important, is that there's an interaction between the even Weyl group and then the groups obtained by looking at G1. Okay, a lot of details. So I also want to mention that this sheaf cohomology functor is associated also with the relatively algebraic cohomology. And so you get a nice spectral sequence which goes from the G0 cohomology with coefficients at M1, and also this induction, and then it goes to the B cohomology of M1 and M2. All right, so this is it's a standard construction. You just use a Grothendieck construction to actually get this. Now, what is the byproduct of all this? Well, the byproduct is we can actually prove the BKN conjecture from 2008. I was really proud of myself. I was able to get an emoji to work in tech. So here's the emoji. All right, so this is a statement of the conjecture that I presented beforehand. And how was this proved? It was actually proved by using the spectral sequence that I mentioned before and using the cohomological interpretations of the Poincare series results sort of back in the previous slides. So using this result too. Okay, so this result basically says that for the trivial module, the spectral sequence collapses. And that turns out to be good enough to actually prove the surgeon. Sorry, I'm taking my slides. Okay. All All right, so let me just talk briefly about new directions. CJ Lai, Rick Wilbur, and I are actually working on a category OF. So we have a triangular decomposition. We can actually define a category L for this triangular decomposition. It turns out to be a very interesting category, especially because it's not like relative category L, like for complex semisimple algebras. This F turns out to be rather difficult to work with sometimes, just because we're not working with semisimple representation. It's small enough, so we're hopeful that we can actually get some results which relate this to other types of categories in these superalgebras. So what we do know is we know that this is the highest weight category. There are possible paternalistic theories. There's cohomology, so stay tuned. And it turns out that if you want to know the x between the dermas, this is a standard result that you just have to look at the n plus cohomology with coefficients and mu, and just look at the number of times the simple module over F appears in the sock of this module. So this is an equivalent interpretation of this X group. So with the ordinary category O, you would replace F by T here, or F by L, where L is a Levy subgroup, and then you get a similar type of result. Now, when L mu is finite dimensional, then this is sort of related to the Constant's theorem for the algebra cohomology. And so David has actually looked at this. He gave a talk on this a couple weeks ago. And he's actually given a complete calculation for when L mu is actually equal to the trivial module. So it turns out that this calculation is quite difficult. It's quite complicated. And part of the reason why it's complicated is that even for finite dimensional representations for superalgebras, there's still non-trivial extensions that can occur. So it's not like with ordinary, like complex semisimple algebras, we have completely reducible for finite dimensional modules. So for superalgebras, you have this added level of difficulty that you have to deal with. Okay, so I'd like to thank you for your attention, and I will leave you with some references on the work that I presented. Okay, thanks. So Brian, are you going to tell us how to define atypicality for type P?
Type P?
Or type P, are you going to tell us how to define atypicality?
Maybe one of various possible definitions, but yes, I am going to propose a definition for type P in a few weeks.
Excellent.
I have a question for you, Dan.
Sure.
On page 23, you had a theorem that you had to exclude type P, at least if n was at least 4.
Yeah.
And then on page 27, it looked like you might have used that theorem to prove the BKN conjecture. You didn't say that Pn was excluded, is that right?
Yeah. So I shoved that under the rug. You're absolutely right. Okay. So the point is in type P, it's type 1. So you can use Weyl and Nakano to handle the type P situation. Okay, so it was excluded beforehand, but you can use an alternative argument to handle type P for this theorem.
Great. Thanks for clarifying that.
Yeah, thanks for asking. I was going to say something, but yeah, kind of slipped my mind. So thanks. Very good catch.
Almost like pre-pandemic time. Using the wall. I just got